Okay. So what do I want to talk about today? So this is probably going to be a relatively short stream. I just wanted to kind of get back into the swing of things. So I apologize to Brian McKenna, who's probably hoping that I will / raid his channel after this and dump everybody on him at 4 p.m. I don't think I'm going to make it that long. It's like 100 degrees outside, or Fahrenheit. I'm in the U.S., so I'm not like boiling. But it's ridiculously hot outside. My air conditioning broke, so I'm under a lot of hot lights. So I think I'll probably only make it a couple hours. So I apologize. So let's see what we can do. So the project that I had in mind was there was a blog post by Bob Atke at bentnib.org where he did a post on authenticated data structures as a library. And he did it in ML. And I'll paste the link to the chat. And what I would like to do today is see if we can mock that up in Haskell. And I'll maybe use Backpack to do it just to see what we think of the API there. And then maybe do a more Haskell-y version of it and see which one works out better. I have a general sense of where I think this is going to go. I don't have all of the kinks worked out. That work for folks? All right. So folks can try and follow along from his thing, but if you do that, you're going to have a hard time following the stream. So I'll just try and reinvent the gist of it as a module signature. So what I want to build is I want to build an API that looks something like this. I have a signature for, I think he called this Authenticate or something like that, where I have some kind of data type for authenticated computations, some monad in which I'm going, or authenticated data, some monad in which I can do authenticated computations. King of the Homeless, I don't know that I'm going to be able to address that today on stream, so I'll have to catch you afterwards. It probably isn't, now that I'm thinking about it. So I very well may have made a mistake on that one. And I want some functor for this monad. I need it needs to be a monad. So if those of you who aren't familiar, this is a module signature for Backpack. What we're saying is here's like an abstract module. We're not saying what actually instantiates this. And you can't see anything I'm typing because I did not switch the screen over to the coding window. There. How about that? I am supposed to be showing you code bpath, sorry. All right, so we've got a module signature, some data type we'll call auth, a monad, and he uses a data type he calls evidence, but I'm going to try and make up some notion of evident thing, class for evident, and what I would like to be able to do, and I believe like in the code that Bob has, he went through and said like he would have the equivalent of having evidence for pairs and a bunch of things. But ultimately, what I'm looking for is an API that looks like this. If A is evident, then I can take A and build some authenticated data for A. And I can pattern match on it in the monad. And so I guess what I'll try to do today is figure out a few different ways that we can implement this. Like one way might be to say something like, well, I do at least expect that evident is implied by to JSON and from JSON. And that would get me, well, it would almost get me the sum and product stuff that he's got. And I would really like authenticated things to be evident. This is the general module signature I'm kind of trying to program against. Maybe show and read should imply evident. This is the general shape. So what am I going to need to actually type signature? Type this. It's going to need kind signatures because I put one on M. It's going to need type synonym instances because M is only a type synonym, and it's going to need constraint kinds. Maybe not. So that's the module signature I want to try and program against. I'll try it with Backpack and see how we like the module signature version of it, and then maybe see if we can do a Haskell-y, a slightly more Haskell-y version that uses lots of fundeps and things. And then I think this will help me motivate why we might want quantified constraints in the future for things like this evident type. All right. So let's see. Maybe what I should do is break my usual pattern here and set another window up. I could have done a Vim split screen. Yeah. So I'm thinking right here what I have is like a module that is the thing that tries to prove I did a computation. So what was this paper? So there was a paper, I think it was 2013, 2014, where, which is what Bob's article is about. And yeah, sorry, King. I try to do it in lowercase mostly to show people that you can. So in the article, in the paper, what they did was they said, here's a semantics for a language that provides authenticated computation. So on the server, you produce the result and a proof that you computed the result the way you thought you think you did. And on the client, there's a verifier that can take the output of the first program in a proof and validate the proof. And so the proof is a sort of a Merkle tree that tells us, yes, we did the thing we said we did. So for my prover, my auth type here is going to be basically, let's see here. We've got an authenticated. We have an A and a string. The string will be like a hash. M will be just writer. And we're going to write a list of values in JSON. That'll work. And then let's see here. How do we want to do evident? Evident A. So one way to do this would be to say something like this. Type evident. This would let me use a constraint for this, and then I could say there's some sort of maybe JSON. Prove that that auth is also evident. So what I'll do is I'll import my data constraint library, which provides us with this entailment and dict thing. So in general, what I'm going to wind up with is here, the auth data type is not actually an instance of both from JSON and to JSON. But the prover doesn't actually need to be able to come back from JSON. It only needs the ability to embed. The verifier is going to need to go both ways. So let's see. So in this case, type evident. Let's go back up here, fix this up so the screen actually fits. All right, there we go. Type evident goes from star to constraint. We'll fix that up after. So type evident is we're just going to use 2JSON for right now. And what I need to do is I need to be able to convert auth A to JSON. I don't need the ability to do this in general. So 2JSON auth somehow. The authenticated version of a data structure is just going to be like a hash of the stuff that's here. So we're just going to spew that as the... Can I review how constraint works really quickly? Sure. So there's a data type in data constraint, which is I just called dict. And it goes from constraint to star, where dict takes any constraint P you want and holds on to it. This is kind of a generalization of the pattern of where you can say data or dict A here's a proof that A is a ORed instance or something like that. This is just a generalization of this to allow you to work with any constraint now that we have constraint kinds. And then there's a new type that I have in there, P entails Q, which is just given a dictionary for P, given P, I can build a dictionary for Q, and this is sufficient for me to do things like ORed A entails eq A, or ORed A entails ORed list A, or ORed A entails eq of list of A, and all you have to do is say subdict and then let GHC type check that. So this would be asking GHC, please prove that given ORed of A, I can give you eq of list of A. And then what I can do is I can pattern match on this thing using a little combinator that I provide in there, which says, given P and the fact that P entails Q, if you needed Q to build an R, I can build an R. And this is something like subdict. And then doing this actual construction is really kind of cute in my eyes, because what it does is it needs to, in order to do this pattern match on sub, it needs a P, but I have a P. It's coming into context right here. So I take this P, feed it here, so that I can use that to get a dictionary of Q. Then I can pattern match on the Q, which brings the Q into scope. The Q that is brought into scope is the thing that I can use to discharge this obligation that lets me use this R without a Q out here, and then I can return it. Okay, and so I can use this to do all sorts of things that need, say, eq of list of A, if I knew ORed of A. And so it doesn't seem terribly exciting that one might be able to do this, but it lets me plumb around information like this evident thing to situations where I would not locally be able to prove it. So what I want to be able to prove up here is that there is some type of evidence that is weaker, potentially, than to JSON and from JSON. It's at least entailed by them. And that auth satisfies this notion of evident. And that this notion of evident that I want to use is enough to build an authenticated data structure and to pattern match on it in my monad M. That's the gist of what I'm trying to do. All right. So that's the very brief recap of Constraint, which is probably too brief for people to follow along if they haven't seen it. So I have a blog post on what constraints entail from 2011. There's two parts to this series. This was discovering and building this data type, which has been incredibly useful to me. It's changed the way I write Haskell a bit, and unfortunately in ways that make my Haskell rather difficult for other people to read. But I just pasted a link to it in the chat, and the second part can be found from there. So that has the review of where dict comes from, and some properties of the entailment operator and stuff like that. But entailment there forms a category, and we can do all sorts of fun things with it. I'm forced to use this right now. I will later on in this today, hopefully we'll come up with ways around this or get a sense of where quantified constraints could make the need for this go away. That's what I'm hoping. I don't actually know where this is going yet, though. So we'll see. So here's my authenticated data type. I need a writer, so import control monad writer or trans writer. And maybe I shouldn't be using writer because writer is too lazy, but I'm going to use it anyways. And then I need a proof that JSON is enough. So to JSON and from JSON A entails evident A. Just ask GHC to figure out if you were given to JSON of A and from JSON of A, could you prove to JSON of A? And then eauth is me asking for just a dictionary of evidence for auth of A out of the box. And that's just, hey, GHC, is it possible? And yes, quantified constraints will hopefully clean this up. So I'm hoping to use this today to help motivate why we care about quantified constraints a bit. I did a little bit of thinking about this before the stream. I have not actually fully fleshed this out. So here's like an authenticated computation. If evident A, I'll give you A to auth A. What is that going to look like here? I'm going to need something like, I need a crypto library of some sort. What do we want that does hashing? There's crypto hash and crypto night, I think. Let's see here. I want to think the commenter's like hash lazy. All right. And that's going to give me a digest for a particular crypto scheme, and I can just show it. So if I were to like show hash lazy hello, this needs to be a byte string. All right, that looks like a hash to me. We'll just make a little combinator to help me do this. And all I'm going to try and encrypt right now are going to be JSON values. So there'll be something like SHA-1 of some particular value is going to be, let's show hash lazy encode my value. All right, so this is taking a JSON value in ESON form and just giving me a hash of it as a string. And yeah, it's, to be honest, BPAF, why is it sub? I think it was subsumes or substitution, and it was the first name that came to me in 2011. I've largely forgotten my original reasoning. So to authenticate a value, what I'll do is I'll take an A and I will SHA-1 the conversion to JSON of A. And then to pattern match on an authenticated data type, what I will do is I will take an authenticated data type and give you a value in my writer by, writer, scribbling out, here's the value, and then adding the value that I just, or that is the encoded version of A to the log of stuff I've touched. All right, so this should, in theory, implement this whole API that we have up here. We have a notion of authenticated data structure. We have a monad in which we can do computation, which is going to scribble out a log of all of the authenticated data structures we've matched on. I have no ability. You generally have, if you were to write abstractly against that module signature up above, you have no ability to like map or do anything with an authenticated auth A, other than match on it to get an M of A in the other end. And maybe to JSON from JSON isn't the best API. Maybe we can go just through like show and read. But let's just start here. So that should be my prover. Let's see if I can type check it. I'm going to need some extensions. I think it'll just be that in constraint kinds. We have a prover. All right, I have no idea if it's going to actually do what I want. But if I were to build, I don't know, an authenticated auth 12, I didn't build any ability to show the things. For right now, I'll just derive show. And then if I were to unauth it, we've accessed it and we have logged the fact that we touched a number. Okay. So now that we're able to produce a log of all the authenticated data structures that we have touched, let's see if I can do this with auth. The key is that when they're recursive, the authentication for an authenticated data structure itself will just be the hash. So if I have a tree of these, I'll only actually have to I'll only have to encode one layer of auth. So typically you might be dealing with some sort of like Merkle tree or something like that. Like here's my Merkle tree and it's got at its tip, it's got some values. And for my bins, I'll have hashes of, or not hashes, I'll have auths of Merkle A, auth of Merkle B or something like that. Or maybe we want to do auth as layers on top of a free Merkle or something like that. And so the idea is that by accessing the tree, what I'm going to be doing is I'm going to be going through layers and layers of auth, which will be scribbling into my log a bunch of objects. Let's see how it goes. All right, so we've got a prover. I need a validator, I guess. Validate. What do you want? Verifier. And let's see here. So here we're going to do the same API. But now I want like my authenticated data types to just be the strings. And but now we're gonna, our monad is going to be a little bit different. Instead of writing a log, we're going to consume the log, and we might blow up. And I need a class that has exactly as many arguments as to JSON and from JSON, so I'm going to use the instance hack. to make a slightly better type synonym. And I really want to use that same SHA-1 function. So I'm going to steal it. Import crypto hash. We have a module. It does stuff. Doesn't need anything fancy, right? Needs data ASON. And the prover can just import hash. We don't need crypto hash. We do need data ASON. Okay, so now SHA-1. It's coming from a common place that we can use. And now we can just say, hey, to auth, using the full power of all evidence, auth is auth.sha1.to.json. Yeah. All right, so we're going to take our JSON value, or take our value, convert it to JSON, then SHA-1 and hash it, and then that's my authenticated value. To unauth, here we need to do some magic, right? Because we have A is evident, and I have an auth A, but I need to give an M full of A's. I need to give a stateful computation that's going to give me back an A. But I only have a hash of it. I only have a hash of the thing. So here's the magic moment that makes the whole thing go. And Swish, there's some video stream compression, but it's I decided to try and stream at pretty high bandwidth just to see how clear I could actually make the stream. And in theory, there should be video settings to turn yours down. All right, so with our unauth, what are we going to do? I'm going to unauth on some authenticated H. It's going to be a state T computation. It says, well, if there is a value at the front of the chain of evidence that we have, and the SHA-1 of it is equal to the hash that I expect, yeah, that'll work. Then first, try and convert from JSON. I think it's from JSON. Data JSON, T from JSON. What's a result? A result is an error string or success. Okay, so you're not an either and you're not a maybe. So I'll just have to convert from you by hand. If anybody knows if there's actually a combinator that just gives back a maybe result out of JSON, I'll just use that instead. Otherwise, I'll just manually pattern match on this thing. And then in every other case, whether we ran out of stuff or we had the wrong hash, whatever, we're just going to fail. And since when you're coding against the module signature, you don't know anything about this monad, you have no ability to recover from failure. I think I might have just implemented the whole verifier. Oh, sorry. It looks like I don't have the transcoding. I am just a Steam affiliate, not a partner yet. Let's see here. So what do we have? We have a stream here. We're going to need some... We need hash for SHA-1. We're going to need data JSON because we have values. We're going to need control monad trans state in order to have a state monad. And we're going to need to, I think that might actually be everything. Did I get that right in first go? I'll be amazed. I didn't. Okay, good. Lambda case. Byte string to maybe A is pretty darn close. But I need to go from a value. So you need lambda case. We're going to need undecidable instances because of the instance hack. Because I'm on GHG84, we're going to need mono local binds now because this thing is no longer free for users, which really annoys me. I used deriving to JSON and from JSON, so we're going to need generalized new type deriving. And I really don't like putting multiple pragmas on a line, so. What else are we going to need? Flexible instances. From JSON helps to not randomly script cases. To JSON is not a unary constraint. Oh, deriving to JSON from JSON. Hey, check it out. We have a verifier. So let's see how we would use this. Load my prover. So we had a really cheesy authenticated computation. This says that I can, if this was my chain of evidence, I can get 12 out. All right. So if I were to run state t, what was the computation again? Unoff, auth 12, bind to unoff. And the starting state that I want to have looks like that. And I want to get back a maybe int. Integer. Where did I screw up? String. Set minus x overloaded strings. Integer value with value. What do we got here? Oh. Exec or eval. Just 12. Hey, check it out. We got it. We've got proof. It was able to construct this 12 even though auth didn't hold on to it. It was able to reconstitute it out of the chain of evidence that I was going to get a 12. Sweet. So we were able to write a piece of code, run it in 2 different contexts, get the same computation to do the same thing. So in theory, what you would do is you would then take your code, write it abstractly against the auth module signature, and then you'd be able to instantiate that thing 2 different ways. One's against the prover and one's against the verifier. And so what I should do is, since I've written a few little things here, let's see if I can throw this in a repo, put it on Git, and let other people take a look. And then I'll take a 5-minute break or something like that while I grab a Diet Coke or something and get out of these lights. That work for folks? All right, so get init, get at everything. GitHub. Create a new repository. Auth. Public. Do nothing. GitHub commit auth. Okay. So for those of you who've been following along, you should be able to pull from there to actually get the code that we have so far. And I'll take about a 5-minute break, or maybe less, and I'll be right back. And then we can dive into questions about what we have so far. back. Can people hear me? All right, I have confirmation from Discord. And Twitch is back. All right. So far, what we have is a pile of Haskell code that doesn't compile with anything yet. Well, I guess it compiles locally for me in GHCI, but it's not really set up so that anybody else can build it. So what I should probably do is build a little cabal project for this to demonstrate how to build a small backpacked cabal project. And then I have a whole pile of issues here about how to, whether or not Backpack is the right tooling for this. So maybe we should try this without Backpack, see if it's better or worse. I don't actually know the answer there. Whether to JSON is the right tooling. Whether something like even just going through show and read would be better and worse. I don't know the right answer there. What other things do I want to talk about? So let's make a parking lot of topics, I guess. I'm good. Well, no way, just drag me a Diet Coke while I was out. And if I dragged a fan in here to try and deal with the fact that my air conditioning is down right now. If the fan noise is too loud on stream, let me know. I lost my Twitch chat. But no, there it is. All right. So what was my parking lot here? So we have is to JSON from JSON the right evidence is what other topics did we mention? Backpack or not Backpack. I mean, not using Backpack would make this thing feel more Haskell-y. Using Backpack gives me a degree of safety that I can know that you're not using any of the features of state and writer that I didn't plan for. Any other notions that we want to do? Oh, and building backpacked cabal configuration. So let's first get this thing all the way to done in the form it's in right now. Oh, and I guess we also have the parking lot question about can quantified constraints clean this crap up? Because we haven't actually tried writing against the module signature, which is going to bite us in the butt later on. And I guess this kind of all ties into a question. Okay, so building a backpack cabal configuration. Let's go actually get that part right. I'll just grab a, I don't know, cabal file from somewhere. Version 0, BSD 2, I like 2. Cabal 2.2-ish. I think I don't need the greater than. License me. Very much experimental. Auth. We wrote it now. I'll put a period there to avoid the complaint that my description is not longer than my synopsis. Tested with is not actually required for anything. There's no fancy anything yet. Source repo. We don't have a custom setup. We have no flags. We do have a library, which is going to be annoying. Cabal version has to be the first line? Since when? We need base, we need kryptonite, we need ASON. A, B, C. That's lame. Do I need 2.2? I can use 2. Haskell source strs is local. I don't have anything in it. All we have so far is a module. So ADD Sidekick. The use cases for this so far are basically what you would have is you have a server that can turn around and give you an answer and a hash that you can then run the exact same computation on a client and then validate that the server actually did run the computation that it told you. The difference is that the certificate that you're using is sort of like roughly going to, if you have like nice big trees and stuff like that, the certificate will be roughly log-ish in the size of the computation performed. So it's got the sort of same flavor as the Merkle tree kind of proofs of why Merkle trees are nice. So you kind of pay for the depth you chase down when you're running through a data structure. I'll try and maybe build up a example to motivate all of this stuff. But there's the original paper provided much of that. So what do we have? We have a library. We have our exposed modules will be something like what? So far we have hash. I guess we just have the common stuff so far. That has hash in it. We're going to need lots of annoyingly little libraries. Don't have any test suites. Library signature. I don't need the signature as a library. Prover. Build depends right now on ASON, base, and kryptonite. And my common library. And it exposes prover. Library verifier. ASON base. Well, it doesn't actually depend on kryptonite directly, does it? It only depends on it through common. Common, exposed modules, verifier. And let's build a little. I need to actually start making these live in separate directories, huh? Make dir common, move hash.hs to common, make dir auth, move auth.hsig to auth, make dir prover, move prover.hs to prover. See, if these lived in the same directory, you start getting all sorts of weird linking problems. Move, make dir verifier, move verifier. Just to the verifier subdirectory. All right, now we've got little subdirectories for all the things. Digital image. Should you use a list, a vector, or an array? Depends on what you want to do with it. If you want to const and unconst, you probably should be using a list. If you want to do all sorts of operations and then hope that stream fusion kicks in, then you should be using vector. If you know pretty much operationally what you want to do, and you're going to be keeping your data flat and then just kind of peeking at every once in a while, then probably an array. But if you're going to be trimming it and whatnot, then maybe go to vector anyways. What do we have here? Off that cabal. Go pull it out of there. I'm just gonna be a bad Haskell citizen and not put bounds on things yet, because I don't really know what they should be. Common, prover, verifier. We have a library for auth, but it's kind of useless. It's just the module signature. But when we go to write other libraries that use the prover and the verifier, what we'll do is we'll use the auth-ders, auth.hsig, instead of using prover and verifier directly. All right, so we've got common. All right, that seems to be a legit cabal file. Cabal, new build. See how much I screwed that up. So auth is building 3 libraries. This is actually demonstrating part of the problem with using Backpack, which is that right now these would have to be 3 separate packages. Because we, if you wanted other people to be able to program abstractly against the API, you'd probably have 4 packages, because you'd have to have the auth signature that you're going to build against and stuff. And so there's a guy, Francesco Gaz something, FGaz is the handle he uses. He was working on getting us multiple public-facing libraries in Cabal this summer, which should make Backpack much, much more usable. I did not really plan for this session to become a sort of Backpack advertising session, but it seems to be, which should make Ed Yang very happy. All right. What do we have here? This is still building, but it's actually building. It has everything. Start doing some housekeeping. Git ignore all the stuff. That's fine. While we're waiting for that, let's get us a README and do all the boring crap. Hey, I need a README. I don't have any of this stuff yet. Contact information, I'm still me. Sure. And then when we get Travis running, hopefully these shields will start working. In the meantime, I think I can comment them out like that. VI changelog, version 0. Ooh, don't add that. Did I not add the ignore of this new style? That was dumb. Get RM, this new style recursively. Why are you not doing that? How do you remove something that you staged but don't want? Do you know what I mean? And especially people, that is one of the questions that I kind of have sitting over here in the parking lot. Is to JSON and from JSON the right form of evidence? They were just the first thing I latched onto. Read and show is probably fine. Get reset. Thank you. Get add everything. So they've been moved. I've added a README. Untracked files. Get reset worked perfectly. All right, and of course I pushed before I even tested to see if this thing would actually build. And why did we wind up incurring a dependency on Foundation? Oh, because of Kryptonite. Okay, fine. Now I understand the comment about Foundation. If anybody else has a lighter weight thing that I could use that would get me SHA-1, I'd be perfectly okay with that. CryptoHash just SHA-1. Well, that... init context single pass hash lazy gives me a byte string to byte string. Well, that is really easy to use. Okay, I will use that instead because I'm not really wedded to it being Kryptonite, and that seems to be slowing down the builds quite a bit. Just test the install of this CryptoHash SHA-1 library before I dive straight in. Hello, Clark.io. Clark.io. I appreciate the raid. Let's see. If I can keep your audience happy. So what we have so far, for those of you who are just joining us, is we started building a little library for authenticated computation in Haskell, based on, there was a paper in 2013, 2014, which said, hey, look, if you were to implement a programming language which had these semantics, you could have the server produce the result and a certificate of the result, such that a client could then just run the same computation with the certificate and validate that the server did what it told me that it was going to do. And it works by sort of building these Merkle trees of what the computation is, and then pattern matching on the when you're doing the construction, you're producing the chain of evidence, and when you're validating it, you're just consuming the chain of evidence as you go. And so it works for much the same reason that Merkle trees work. And so we've been going through and trying to model this using Backpack in Haskell, using this as a little bit of a tutorial on how Backpack works. And that's pretty much, I think, where we're at. So for those of you who are just joining us. And for those of you who are just kind of tuning in for the first time, just so you know, I don't know how much the Haskell regulars know about Twitch, but if you aren't familiar with Twitch, you can, and you are I believe if you are a Amazon Prime member, you're allowed to gift a subscription. It costs you nothing, and it gives me like $2.50 or something. So if you see the gift a sub button at the top, that's what that's all about. So that's my one pitch about gifting subs. I will go back to rambling on about technical stuff. Okay, so CryptoHash SHA-1 worked, or at least installed. Let's use it. It should give us a lighter build than the CryptoHash, or than the Kryptonite thing. I apologize, Vincent. I just don't need all of the stuff. So what do we need? We needed to hack up the common lib to build a lighter weight SHA-1. So this is crypto.hash.sha1. And we were using hash lazy before, which takes byte string to byte string. So we're using this little function, which seems to be here in the new API. I don't get out a digest SHA-1, I just get out a byte string. And then I'm converting it to a string, which should be good enough for me. Alright, well that was easy. Now Cabal new build should run a little bit faster, because it doesn't have to install the foundation stuff. And then I'll push that up to the repo. Yeah, it's a slightly smaller dependency list for a tiny, tiny little library. And then by the time I shared a link to Bob Atkey's Authenticated Data Structures thing at the beginning of the stream, but of course that's not useful to people who are just joining now. So let's go back. So here's the here's a post by Bob Atkey from about a couple years ago. And there's this Authenticated Data Structures generically paper, which is the origin of this idea, which was in that paper, what they did was they described a language that had the semantics that they wanted. And in Bob Atkey's post, he did the same thing that I thought about when the paper came out, but I didn't do, and he did, which was to write a little library that implemented the semantics of the paper, rather than require you to build an entire programming language. So this Miller, Hicks, Katz, and She paper describes a language that looks like OCaml, and then they give semantics to matching and unmatching and all this kind of stuff, and then they have auth and unauth in a way that is recognizable to the code that we have. And for those of you, again, who are just joining us, and for those of you who tuned in a little bit late or just weren't paying attention, the repo that we built about half an hour ago is sitting here at GitHub ecommit auth, and it is going through a series of gyrations that are leading it to it. So I just figured this would be a fun project to get back into the stream with, that you can kind of tackle ab initio without any prior exposure to what I've been rambling on about. And it's sort of a tour of how Backpack can change the way that we might write Haskell, and whether or not Backpack leads to a good API or not is still an open question. I'm still playing with it. All right, so we have auth. For a newbie, link to Merkle data structures. We should be able to pull up Merkle tree and just get the Wikipedia overview of a Merkle tree. the idea of a Merkle tree is we're just going to store a tree of hashes. And so if you have a cryptographically sound hash function, the only way you could really build this hash at the root is if you had all the hashes of all the things below you. So if I were to give you some path into this tree, I can have reasonable confidence that you didn't lie to me if I walk down the tree. So it's part of all sorts of fancy, like zero-knowledge proof kind of things. It's a pretty common cryptographic toolbox. If you're familiar with Bitcoin, it's basically a Merkle list. Every node has a hash of the previous node in it to hold everything together. And so, as in Cache with Cactus, ELI 5 authenticated data structures. So the idea here is that what we'll do is we will write a program in a little subset of Haskell, and then what I should be able to do is run that on a server somewhere, and that server should be able to produce an answer and a certificate about that answer that proves that I did something that I want. And then on a client, I should be able to run that same program, hopefully faster, or without having to like generate all the crap, and be able to use the certificate to validate that the server did what it told me it did. Cabal misses transform. Oh yeah, I probably did need transformers in there. Oh yeah. Did that finally try and build? No, it's still a bit fiddling around with ASUN. We're going to need transformers. Not here, but here. Oh, and we're going to need my constraints library, I guess, as well. Use Cryptographic 1. Require transformers. Let's try that. King of the Homeless. Whoever was interested in local instances, here's your proof of concept. Okay. Yeah, I'm not going to be able to page that in right now. Cabal new build. Work. Okay, so pulling up the module signature of what an authenticated computation looks like. This is the little EDSL that we're going to be programming against. We have authenticated data structures, auth A. We have some monad M, in which we're going to be working with our authenticated data structures. These will be our authenticated computations in Bob Atkey's terminology. We have some notion of evidence, which in Atkey's stuff is actually a data type. And since we're in Haskell, since evidence is going to be uniquely determined for the type, what I'll be able to do is just ask for it to be some kind of dictionary, some kind of constraint that I can pass around. And I ask that currently that to.json and from JSON is sufficient for us to establish evidence, and that auth is evident. And so if given any evident thing, I can build an auth of it, and then I can only pattern match on it in the M monad that we've built here. And Pedro, the entailment operator comes from the constraints package, and there was a what constraints entail article from 2011. This came up earlier in the stream, but I will paste it again because we have a whole bunch of new people into the stream right now, which provides sort of where that data type comes from and how you could use it. So I wrote this immediately after Max Bolingbroke gave us the constraint kind in GHC in like 2011. And so could EAuth be defined as instance evident auth A? It might be able to. So the concern that I would have is that I can't write an instance necessarily for a type constraint. So I would have to demote evident from start a constraint as a type to be a class, and then I would have to make an instance of to JSON A from JSON A to evident A, and then an instance of evident auth A. And then I would have to rely on these things, say having overlap or overlappable, which isn't quite the right semantics that I want, right? Like, in some ways, when we did the prover earlier, we said that the amount of evidence that I only need the ability to convert things to JSON in order to work with this. And the auth data type that I built is only an instance of to JSON. It's not an instance of to JSON and from JSON. And so here, this is evident. And given to JSON and from JSON, of course I can satisfy a to JSON constraint. And we can build one of my authenticated things by holding on to its hash and storing the value, and then matching, I convert the value to a JSON. Okay, does that resonate at all? And yes, this may not be the best first moment look at Haskell. This is sort of a tour of a relatively new feature in Haskell and then using it to implement a library in a funny way. So right now what we're exploring is using a feature that has been recently added to Haskell called Backpack, which gives us ML-like module signatures. It was written by Ed Yang has been the person championing it of late. It was Scott Kilpatrick before that. And Ed Yang did a lot of work to make it viable to work with Haskell's type class mechanism and all that kind of stuff. Okay, so we've managed to build our prover and our verifier, and holy crap, the whole thing compiled. The license file refers to a license I don't have. Now I do. We wrote it here on the stream. All of Twitch. No. Just me. I did it. I wrote it all. Alright. Git add license. Alright, in theory, I haven't used Backpack. Could you show how to use the libs? Why use... I actually... the VI that I'm using is Vim. I type VI because it's one fewer keystroke, and I've been using those keystrokes for 30 odd years. And now that we have GHCI running and stuff like that, I can start GHCID once we want to move off of the backpack. Once we want to move the parking lot off of above me here. Okay. What do we have? So we have the prover, which is basically just using writer to scribble out a log. And we know we have evidence for JSON and evidence for auth and all this kind of stuff. And then we have the verifier, which instead of writing the log, consumes the log. And an authenticated data structure here is just the hash. Maybe I should make a better data type for hashes than string. Auth. Not auth, it's common hash. Data hash or type hash equals string. There. That way I can convert it to byte string really easily. Sweet. And then we'll just mangle the prover. And SHA-1 of 2JSON of that. And we'll mangle the verifier. And what do we need here? SHA-1, 2JSON, and instead of auth holding onto a string, it's just going to hold onto a hash. So start getting a little bit of slightly more informative types, even if they're not terribly Great. Data byte string is not known yet because I didn't tell GHC about byte string. This will let me not toss around strings, but arrays of bytes. See if we have the prover and the verifier. And yes, I have not forgotten about your how do you use backpack question. I'm just trying to push the stack or pop the stack enough to get there. 2JSON of hash is not there. Where was it? It was common hash. Fine. We'll make a new type for hash, and we'll call it a hash of a byte string, and then we'll put that in hash, and we'll make an instance of 2JSON hash where, what do we want here? I don't even remember what's in the 2JSON instance. Wait, I can't derive it because hash byte strings are not JSON. Data.json instance 2JSON. Or info on 2JSON. 2JSON needs to take an A to a value. Info on string. What does string do? Hold on to text. Of course it does. Because why not? Let's showcase how bad Haskell is at mangling text because we have 4 different text types. So 2JSON hash. What are we going to do? We're going to take hash this string, and we're going to convert it to a string of data.byte string to string s, and then text that from string. Yay. This is from JSON hash. Anyone remember how to write a manual from JSON instance? This was not my best idea. I should have kept it with string. You know what? I'm going to keep it with string because that was super easy. A hash is a string. And I don't have to freaking fight with it. And byte string can go die in a fire. And we'll keep our example easy. If I was performance minded, I would care. But I'm trying to get the idea across right now. I think I was talking about string, text, byte string, and then whether or not I was lazy. So, okay, maybe not exactly 4. And yeah, I used to use screen way back in the day, like mid-90s. I've gotten out of the habit. I could put tabs here and stuff, but mostly just wanted to keep my tools pretty minimal for the stream. Verifier, prover verifier, cabal new build worked. Okay, so I didn't necessarily like the 2JSON and from JSON. This was the observation that I made earlier on, that maybe the authentication signature, instead of 2JSON, it should just be like show. From JSON should just be read. I'd be okay with making that switch. What do you think? Let's try it. So how does the prover get mangled? Instead of holding onto a writer of list of values, we're just going to hold onto a list of strings. 2JSON show for auth is just going to be show. We're going to delegate it to h, to the hash. given show and read, I can prove show. JSON can die. There is an instance of show for auth. Yes, that's true. Evident A gives me auth A. So that's fine. I don't need to convert it to JSON. I just need to show it. Prover doesn't change much. The verifier, on the other hand, also doesn't change much. Show and read. But I have to be very careful because now these want to derive, and the derived versions of them are going to want to put the tag in. Instance show for auth A, where shows prec d auth some hash is shows prec d the hash. Instance read auth A, where reads prec. I think that's it. Info on read. What do we have? Read GHC read read prec. Read prec is actually a thing I can fmap over. So there's two APIs in text.read. There's the traditional one, and there's the one that GHC support. GHC supports this read prec thing. I'm just going to use read prec and then map over it. The other one is based on ancient horribleness and has, I believe, worse asymptotics or something. Auth show read state, we're good. Read A, show A, read A, show A. To JSON is now just show. And instead of from JSON, all we're going to do is read maybe. And now I've got just A to that, and so all I just need to do is like kill all that. Okay, so in an authenticated computation, now we show authenticated data structures just as their hash. We read them back to really make this legit. So this is actually legit code. Maybe what I could do is like add an instance of is string for auth or something like that. But I'm not going to because it would only work on one side. We have evident. We can auth and unauth. I think we might have fixed the JSON dependency. That's gone. Oh, read maybe is I need tuple sections for verifier as well. So I decided to be clever. Prover. Yeah, so I started with JSON, but I didn't really like it, so I just decided to rip it out. Because there's an observation, of course, that JSON is really bad at dealing with some types. Like, derived JSON doesn't work automatically for everything. So I was using JSON as a thing that I could just get everywhere, that I could compute hashes off of. And I didn't really need anything other than the ability to go into it and come back out of the format. We could use binary. The problem is that data.binary doesn't have a write-only form, which would be suitable for the verifier. And I didn't really want to make an illegal binary instance, because then you might be able to care a little bit more about whether or not you're programming against the verifier or the prover. And why isn't read maybe in the prelude? Because people in 1998 didn't think about that. And in the meantime, people started complaining very loudly whenever we added things to the prelude, so we're very, very cautious about doing it. And they're not complaining loudly without reason. I don't mean to sound like I'm dismissive. So what was that whole JSON stuff I did previously? Right before the stream, I just said, oh, maybe I'll just use JSON or something like that as the way to serialize in and out. Partially because that was the way Bob Atke did it when he wrote the ML version. And then as I was writing it, I was kind of thinking, well, JSON isn't really adding much value here, so let's get it out. Let's get it out of there. So I think to JSON and from JSON is not the right. I think the answer here is no. Is this the right form of evidence? I don't think so. And we now have a backpacked cabal configuration. Check. We haven't actually written anything against this module signature. Am I a GHC contributor? I believe I chair the core libraries committee, which is like all the stuff around the compiler. So I try to treat the compiler as given and then build all the stuff around it that we kind of need as an ecosystem. Do the preludes discussions happen on the library's mailing list? Most of the public-facing side of things is definitely on the library's mailing list. There is a core libraries committee mailing list, which I don't know if I don't remember if it's private or public. I think it might be public. You probably can get the archives. But it's where, like, when the core library committee needs to go behind closed doors and deliberate about stuff, like there's usually a poll and stuff like that. Whenever, like, something doesn't reach a clear consensus on the library's list and we need a way to move it forward. So, what do we have here? Problem with list of char against value. Prover, I probably have some residual bit of ESON or something. Where's value floating around here? Writer show. Prover. SHA-1 takes a value. Did I leave that off? Where was it? It was common hash. This is not a value. We just take an arbitrary string, I guess, and hash it. What else did I screw up? Verifier. Man, I'm all over the place. Verifier. This is no longer a list of JSON values. It's a list of shown strings. And then duplicate instances for the verifier, because there's no point in putting these show and read instances here if I'm going to immediately put manual ones. Variable not in scope show prec, because I'm an idiot and forgot a S. Shows prec. What about the space link associated with writer? I mentioned earlier that maybe writer is the wrong thing. I think when we go to do a manual version of this later that's like maybe a little more traditionally Haskell-y than using backpack, maybe we'll fix the writer space link along the way. Remind me if I don't. And I'm using lazy state and lazy writer because I didn't really get into a super performance-minded space when I was starting to put this together. Hash is still sending us input. Wait, cabal is sending its input to ESON in code. Get -r ESON. I'm using the verifier, I'm using the prover, and using hash, or common hash. ESON can die, I don't need it. And this is getting to be a pretty small API actually. Auth.h cabal no longer needs ESON. Alright, I wish I kind of had that thought earlier because we would have had a much smaller dependency tree all the way along. Oh yeah, common hash. You're right. It is being sent through encode. Sorry, I missed that. Hash. All I'm going to do is just pass it along. I might need to convert it from string or something like that. Crypto.hash. SHA-1. What does hash lazy want? Import data.bytestring.lazy as lazy, or lazy byte string from what did I screw up now? Common hash, line 11. And of course, now I need byte string again. Then I'll push this up to the repo as soon as this actually builds again. And we will have removed all the JSON-y bits. Is it pack in byte string? I always go through lens. It's pack, but pack takes list of word 8s. Data byte string UTF-8. Where's data byte string UTF-8 come from? Data byte string UTF-8. UTF-8 string. Contents. Yavor. Data byte string lazy, UTF-8, I'll use you. Pack up the cabal file one more time. UTF-8 string, I don't actually need to. This is in common hash. Data byte string lazy, UTF-8. We're going to build a UTF-8 byte string. That way, in case this string that we've built contains exotic characters, it doesn't blow up. Pimple's, the Haskell is used a lot of places. Historically, it's largely been used where correctness really matters. More recently, people have been building everything from CRUD apps to like random Amazon Web Services and stuff like that in it. For me, I work for a company called Digital Asset. We use Haskell to build a smart contract language that we have that runs on a blockchain. There are several of these beasts. Ours is peculiar to our domain. Sort of blockchain adjacent tech. There's a series of blog posts on the Digital Asset website that describes kind of how we differ from the standard solution. Any recommendations for books and papers one needs to be able to follow the Comonad reader or this Twitch? Oh, that's a good question. It depends. There's from a math and category theory perspective, Comonad reader is pretty heavy on the category theory side. So making it through Audi or Lenzner's book on category theory is probably more useful for reading that than most anything else. I think I gave a book review of Learn You Haskell by on Quora at some point. And at the time, I included a sort of series of next steps about like where to go deeper on Haskell. Is Haskell somehow used for GUI program? There's several different ways to do Haskell for GUIs. There's something called Threepenny, which is I think a little JavaScripty GUI thing. There's React, which is a functional reactive programming web framework, which is very popular these days. So if you're doing sort of like web-based GUI stuff, those kind of stories tend to overlap. I think React is probably the most evolved in that space. They use GHCGS to compile down. It's probably not the most gentle introduction to Haskell. There's bindings to GTK and a bunch of more traditional GUI options that way. Somebody else has some bindings for using Qt. Using its there's a funny like JavaScript glued thing for talking to Qt that there's a library for talking to in Haskell. That's pretty nice. Gloss, if you want to just do graphics. I have bindings to OpenGL. There's the original Haskell OpenGL bindings as well. So GL and SDL2, if you just want to do game graphics kind of stuff, is there as like low-level bindings. So web GUI stuff, there's like whether like just writing things in Haskell and then using GHCJS is a pretty heavy pipeline, but there's also like if you're just looking for something Haskell-like, then PureScript is sort of a strict language that has a very strong Haskell flavor that works pretty well in that space. I don't know. Did I say React? I meant to say Reflex the entire time I said React. I apologize horribly. Sorry, Ryan and company. Reflex, definitely Reflex, not React. I definitely prefer PureScript to Elm, just because I find that Elm puts a pretty low abstraction ceiling on you that can chafe very quickly, and you may not even realize that you're being bounded above in what you can think. Any recommendations for high-level 2D and 3D GPU rendering? So I use, I start pretty low-level when it comes to GPU stuff. So I use the GL bindings that I have. I'm switching over to using Vulkan. We do not yet have a good Vulkan 1.1 binding for Haskell. And we don't have a good like ImGUI equivalent for debugging graphics applications. So I would like to write a pure version of ImGUI for Haskell. You could be able to write one that just like runs inside of any state monad and builds up all the environment it needs, and then would let you basically write pure code, and then when you're done, splat out the ImGUI overlays. But isn't Vulkan even more low level? So yes, low level bindings for Vulkan would be the difference is that OpenGL has the problem that on the Mac side they have just decided they're not going to go any further with it, and it's kind of been locked at 4.1 for a long time. Whereas at least with Vulkan, I can come up with a way to run a compute shader that runs on every platform that I care about. And so if I wanted to have a good high level compute environment, then I would go with Vulkan today. Even if I had to build a layer on top of the low-level Vulkan 1.1 bindings. That's sort of been the direction I've been heading. Do I plan on doing a big Q&A session next time? Last time I did a big Q&A session, it kind of had about half the viewers as a usual coding session, so I think I'm going to try and code for a little while and before I do the next Q&A session. It'll probably be another month or two. Do I find it viable to work with low-level graphics with high-level language abstractions? I do. In some ways, like when I went off most recently and I started playing around with VR, I went and very deliberately wrote all of that in C++ rather than writing it in Haskell, mainly because I didn't want to be trying to fight to learn OpenVR's API and stuff like that at the same time as I was trying to figure out how to fit it all into Haskell, so that I would have like 4 different things I would have to blame. Is it the OpenGL? Is it the GL rendering parts? Is it the OpenVR parts? Is it my Haskell binding to OpenVR? Is it my Haskell code? There's like 4 different things I would have to blame. And so now that I'm more comfortable with it, I would probably just write that stuff directly in Haskell. Haskell will keep using OpenGL even when they say otherwise now. I don't know. They've been kind of down on it for a long time, and they really want to drive people to Metal. And the fact that it's about a factor of 3 or 4 slower than Metal on their platforms is a real reason why I think they're kind of in the same boat that they were when they were trying to push everybody off of Adobe, but I think they're a little less in the moral right. Do I program with other languages? I do. I write a lot of stuff in C++. I write in Haskell mainly because of laziness. Although we're getting really deep into Q&A stuff here. The fact that Haskell is lazy everywhere really changes the story for building data structures for me. Apple does not support Vulkan, but there is a third-party library called Molten VK, which cross-compiles Vulkan down to Metal. And that's being maintained through another company. And so they have open-sourced that, so I'm not so worried about it. That gets me out of maintaining a completely separate pipeline. And yes, feel free to just ask me questions on IRC if you have like narrow questions that you want to ask. Let's dive back into this though before we get derailed too far. All right, so we've decided that we don't like the to_JSON and from_JSON form of evidence. We can read and show. Get diff. Does this all? We've switched everything around. So now if you pull from the repository, you should be able to build off of that. To backpack or not to backpack? That is a good question. So how would this look like in a more traditional form? I would have to like build like a monad auth or something. So let's go look at the auth header here and see what a traditional Haskell version of this would be. Auth. Here we go. In here we just do, I'll just make auth.hs. What do we want here? I want some kind of like monad auth where I have some notion of what is evident for this monad. And I'm going to need a data type for what is auth for this thing. Auth would take evident MA and give me a to auth MA, unauth auth MA to MA. I need evidence that read A and show A entail whatever my notion of evident is. And one of the reasons why I would like quantified constraints here, now that we can see this in more Haskell terms, would be that I would really like to be able to just write something like this. For all A, I can prove to you evident MA. And for all A, read A and show A entail evident MA and monad M. Monad auth M. This would be the code that I would like to write, and we can't quite say this in Haskell today. These quantified constraints don't yet exist. Did I screw that up? Yeah, okay, that's good. And then this would let me kill these lines of code. Parenthesis in eauth. Oh, yeah. So the idea would be that once you had this, the quantified constraints would say evident MA. Evident M auth A, sorry. This would say that auth A must be an instance of evident, and so if you needed it locally, the moment you know monad auth M, you'd be able to derive evident M auth A for every A. And then read of A and show of A would be enough to get prove for you that evident MA, whatever your notion of evidence is. And as we showed before, the prover didn't need auth to be both read and show. It only had the ability to show it. And that was important. So this would be the code that I would like to write. In the meantime, I kind of have to write it this way, which is annoying. So this requires me to manually open up those dictionaries sometimes from time to time if I were to write against monad auth, which we'll see, I think. And then there's other stuff like, so if I really wanted to just be able to say, so auth for auth, I would really like to be able to say monad auth m entails that auth ma to auth ma. But in order to write this today, I would have to say something like case e auth at a of dict auth a. Whereas if I could write with the quantified constraints, this would just be auth. Otherwise, you're going to wind up having to match on these eauth and ejson things all the damn time. Yeah, I'm going to need a for all a there, and scope type variables and all this fun stuff. Read a, show a gives me a to auth ma. Not auth JSON, this is auth for strings. Auths is case e, these aren't JSON anymore, this is e. E show at a. Alright. So now we've got our notion of monad auth. But I don't know I really like this, because now like if I build like monad transformers for monad auth, I'm going to have to build new data types for each one of them. So maybe what I want to do is refactor this a bit. What is possible use case of this authenticated data computation idea? Well, the client having to do the computation again. So the server might build up a gigantic data structure, and then I have the hashes that like validate that this whole data structure exists. And then walking down it might be, I only need to give you the log-ish path that I use to match. So I have like the authenticated data structure where I'm only kind of paying for, here's the proof that I have a little Merkle spine that could get me to the bits and pieces that I'm looking at. So I would only be like, I would have to serialize you the hashes for the large data structure that I built. And then over here I would say, hey, look, I walked this map, and here's the steps I took to get down there. And I would only pay for like the log or something like that of the size of the map in terms of the size of the computational trail. Because I don't need to authenticate in order to build something, I only need to authenticate in order to match on it. So like if we can agree on the map by saying here's the map we've exchanged in previous sessions or something like that, I can say now go look up a key in it, and we can authenticate the lookup. 8.6 alpha with quantified constraints is available at download Haskell. Yeah, there's still some problems, I think, with authenticated constraints, though, which actually I think will keep the thing that I want to have here working. So I'm going to continue to work with 8.4. So I don't really like this API, where right now I've got one auth type. So maybe what we'll do is, let's kick this API around. I'm golfing it a bit here. Authenticated T. Let's build auth itself into a class. And I'm just giving up on the start a constraint, so I don't need the instance hack. And then we'll show, I don't like the name, so ev maybe show a, read a, evident ta, auth is going to be proof that evident t of a, and then this will contain the auth side of the story, evident ta, a to ta. So now instead of auth, we just have t for some authenticated thing. We'll still have auth v or something like that. And then we have eauth here. I think this is okay. Now instead of this being that, this is just authenticated T. So here's an authenticated T, and here we can take T. This is like duplicate, almost like it was a comonad. So here's like our duplicate for any authenticated data structure. And then monad auth M would have associated with it a notion of what auth is for that M. So monad auth TM such that M determines T, maybe. And here unauth auth MA would live and give me an M of A. But now auth is just T. And then like by default unauth would say something like monad trans s monad auth and M is S of N. I don't know here. T is T prime. I guess I can just use this. TA to MA. And unauth here would be lift.unauth or something like that. And this would let me lift over monad transformer stacks by default very easily. Why can't it just be auth A without the pattern match? Where is that? Given that it is a different A, how is the line above changing? I'm missing your red X, Sander. Not quite following. So yeah, so what I'm trying to do is say, what would this look like if we didn't use Backpack? Like we went through all this, like endeavoring to try and build this out of Backpack. And one of the questions I kind of threw in the parking lot way earlier was whether or not like a backpacked API felt cleaner. Because this is a very nice short API, but it's kind of a pain in the neck to use in some ways. I just didn't know whether or not a backpacked API or an unbackpacked API would be cleaner. So I'm having to build up all of the machinery in order to do it without Backpack now, just to see it. So why can't we just call auth A without the pattern match? So the problem here is that here we know read and show, but we don't know evident. And we know that, so by default, evident would be show and read, or read and show. I need to know that I want you to provide me with proof that show and read can prove evident for that data type. But the GHC doesn't know how to use that evidence. So pattern matching on the dict here in eauth brings into scope proof that T of A is evident for T, that we could auth it. That lets me do this auth line. And here I'm using read and show here in order to construct the instance of evident that I can then use for auth. Does quantified constraints supersede the constraints package? I would have thought so, and it turns out no. So there's all sorts of things that we can't think in quantified constraints right now. So you still wind up needing the constraints package. In particular, like just trying to talk about this and stuff like that in constraints today, and quantified constraints today blows up. But I can talk about this all day long. So A entails A is enough of an example. There's some GHC tickets that are currently open. I think Manip and some other folks have been talking about them on the Haskell Lens channel. Because one of the things that I've been kind of hoping to be able to do is once we have quantified constraints, one of the replacements for P entails Q right now, which has that weird structure, would be to do something like subdict, all one word, just to kind of be able to reflect on what it means. This would be P entails Q. I would really like this to work, but it currently doesn't in all the situations that the existing P entails Q works. Sounds like quantified constraints might grow to add stuff like that. It might. I don't know that it can. There's been like a number of like curveballs that have been thrown at it recently. In some ways, the constraints approach is a little more explicit than the quantified constraints approach, so it has the ability to get more help from the programmer. So what do we have here? We have monad auth. So unauth can now run in anything that we have a monad auth instance. Monad auth is going to need monad for M and authenticated for A, or authenticated for T. Authenticated is a long word. Authentic. That sounds good. Pun-driven development. And yes, Simon trying to guess. It's there's a talk by Connor McBride in which he talks about like whenever you interact with GHC, it's like no, let me guess in Simon's cheerful, delightfully British lisp. What do we have here? So we have auth, unauth. We've started to build the thing, so now we just need to build our prover and proven and stuff like that. So maybe we can... I think this is actually sound, what we've got here. So I've got a data type for T, which is authentic T. We know that we can... If A is evident for T, we can embed it. And by default, we'll expect that this to be show and read. Fine. I don't know that we need the default, but the default was just sort of a way to think about it. And then I might be able to say, hey, look, instance or data proof on A is going to be a proof that holds, here's an A and a hash. We'll import the code from the hash stuff from common. And an authentic proof, which says that we can auth just like we did before. Let's go look at the way the prover did it. So in our prover, we just stored the thing, and then we stored the SHA-1 of showing the thing. So to auth, we are going to, here's a proof. It contains the A and the SHA-1 of showing A. And here the type of evident for proof for A is going to be show A. So that's all I need in order to produce evidence. And we needed EV and EAuth, which are just boilerplate, if we did our job right. And these let us know that it is possible for us to auth proof, or we can build a proof of proof from proof. And then, well, I guess what I'll do is I'll just build a new type for prover. A is going to be, actually, we'll build it as a writer monad, but I guess somebody else, I believe it was King of the Homeless, mentioned, well, writer is too lazy, so we'll make it super strict by making writer out of state. And so here we're going to work in give me a list of proofs or something like that, a list of strings, and I'll give you a and a list of strings. And I could just write this with monad transformers underneath the hood, couldn't I? I mean, I could just take the state. Nah, I don't want to do it. I'll do it this way. Monad prover. We'll write it the hard way. This is applicative prover. Let's write a state monad by hand. But I'm not lazy enough to write in pointer. How do we prove that prover is applicative? Well, it's pure A is prover, take the state, give me back this A in the state. That's app. We don't need to write return anymore. I'm not trying to even bother to support anything before 8.4. We can backport it later if people care. And here we've got prover for some computation bind to some future computation is what? Here's a prover. It takes its states and says run the first computation with that. Case ms of I have an answer and I have a state prime. We'll call f on my answer. We'll run prover that with the state prime. Great, we built a monad. We can monad. And then we need an instance of monad auth that produces proof for our prover. Is a QMT from transformers relevant here? Possibly. We could probably have used a QMT or any of the random strict writer things. What do we have here? Monad auth proof prover. What do we need to unauth? And this is going to be prover takes my state. And I don't really like this, but I'm going to just go. I'll const it onto the state, which is actually the exact opposite of the approach that we were taking before. Because here what we were doing is we were writing onto the wrong end. And if I really want to be super duper fast, I need to produce my list in backwards order and then reverse it or something. So here we're just going to produce the action that is... Did I lose audio? Everything got really quiet all of a sudden. I guess not. Why does my Discord automatically join in voice chat? There's two referral links. One is the voice link. One is the text link. I think you just followed the text link. Or the voice link. All right, so we're going to give back nothing and just const A onto my string. Or not A. We're going to const the hash. Oh no, we are going to const the show of my A onto the string. Yeah, I think maybe I should make the Discord thing join the text. The whole reason of having the Discord chat is for the Discord voice chat so that people can ask me voice questions. Although everybody on Discord has been really shy today. And since I've had problems with Discord audio going through to the stream, it's probably fine that everyone on Discord's been shy today. So yeah, if I don't have it fixed by next time, let me know. Monad auth, prover. Do we need anything else for monad auth? I can unauth. But we're going to have to... I'm going to need evident TA in order to be able to unauth, which means we're going to need to write unauth v and unauth auth as well. It's going to be really tedious. Okay, so we have a monad auth for prover. And what else do we need to be authentic? We can build a new type for verify. quantified verification. And this is just going to hold on to a hash. And here we can have an authentic verification. I like the way that reads. Instance authentic verification will be that we have how do we know that this is evident? Show a, read a. E auth is dict. And auth here was the thing that we described before. So in our verifier, what do we have? We auth by doing auth.show SHA1.show. So this is now verification. .SHA1 show, and then we can make a monad for verifier. Verifier of A is what? Well, this is really just going to basically be state T under the hood, but we'll write it longhand because why not? List of strings. I'll make a nice name for a certificate or something like that. That way I can change it later. Okay, so let's first of all, I guess we can prove for all m such that I have monad auth tm. Given an m of a, I'll give you an a and what I'll call a certificate. And prove here is going to take my computation and it will run prover on m, starting from an empty certificate, and this will give me back an a and a reversed certificate. And then I will reverse the certificate myself. But this is just F mapping reverse over that, so we can be clever and obfuscatory. And for right now, a certificate will just be a list of strings. And nothing up here needs to care about that. It's only down here. So we run with an empty certificate, we reverse the thing to get a real cert. Here we run with a real cert, and we give you back maybe an A and a certificate for the rest of the computation. Now we have a verifier, which we can make a driving functor, applicative verifier, monad verifier. Is there a disadvantage to using writer dual string? The main thing was that writer is going to be a little too lazy, and so you're going to build up huge towers of mapends inside of the writer thing. So if you had a strict writer, like not just control monad trans strict, but the writer that is made out of state that somebody else has packaged up somewhere, then you could have gotten away with it. So maybe me going off into the performance weeds is unnecessary. It probably is. Almost certifiably is. But verifier, take state, give me back a just an A and my state unmolested. And here app is app. And the monad for verifier does the obvious things, which is that return is pure, but verifier M bind to F is what? Do something, which is going to be first take the state and in the maybe monad do get A and S prime out of M of S, and then run F on A, run verifier that beast, feeding it S prime, and that gives me a state computation to finish. Okay, so now we have a verifier, and we just need a monad auth instance for it in terms of verification. Monad auth that produces a verification verifier, and here we need unauth. And so this unauth has to do the same thing that we did up here. Verification. And now this is verifier. Other than that, everything else I think comes through unchanged. So now this is starting to feel a little more Haskell-y. So we have a prove function that takes a computation that works for any monad auth and will produce an A and a certificate. Let me move these down to the bottom here so I can see them together. And then I have like a verify function. Take a computation that works for any monad auth TM and a certificate and produce maybe an A. So verify M some certificate is going to be run verifier M with the certificate and validate that we get nothing out of it as a residue, and that's my answer. And then we can be clever using do notation's ability to fail. So we'll run inside the maybe monad. And this will fail if this thing doesn't match the empty list. Writer CPS transformers and writer CPS MTL. Thanks. I knew that it had been packaged up by somebody at some point. So we have a prove and verify. I don't like that name. Trust. This will take and produce an A and then validate as it goes, just to sanity check the thing. It'll run it both ways. Trust but verify this computation will be first trust M, which will produce an answer. I'll produce both A's. So we get the certificate out of trusting it. We get an original answer and a certificate. And then we can verify using that certificate to get a second answer. just give them back. I am bumping way too much. Is that the table? So me bouncing around, or... The camera stand is way too sensitive. The camera is literally just sitting on the back of a laptop that is way high up on the tower of stuff in front of me. So I apologize for me bouncing around. I have an arm for doing this sort of thing. It's just repurposed at the moment, and I'll next time I stream, I should have the arm mounted on something that is not tied to my desk. This desk is getting excessively rickety. So I apologize that I'm bouncing around down there in the corner. Yeah, I guess I do bounce a lot now that I'm looking at myself bounce. All right. Let's see here. Is that a call for a new desk? Maybe. I don't really want to rewire everything, though, so no. Okay, so we have the verifier, we have trust but verify. This is starting to look like it might actually compute something, so maybe we should actually start writing all of the 9 million. So I had a common hash thing. I'm just going to steal this code completely so this becomes a completely self-contained file. So crypto hash SHA-1, byte string UTF-8. We have this notion of an authentic thing. We need data.constraint. And so parse it. So basically what we're doing right now is we're building a little library for authenticated computation in Haskell. Since we've been going for about another hour since the last time I mentioned this, I'll kind of give a quick what's up. So there was a paper in 2013, 2014 or so that talked about like how you could modify the semantics of your language to produce a certificate that it computed what you thought it computed, and then a alternate version of the same semantics that then validates those certificates. So the idea here is that you would then be able to write code that you could then run on the server that's going to produce a little certificate of what it computed, which looks like a little Merkle tree, and then on the client we're going to look at the Merkle tree rather than do some of the computations. Is it ready for a mini demo? We're almost there. Now that I'm sort of building up this sort of non-backpacked equivalent, it should be nicer to demo. I was thinking about how I was going to write a demo thing with the backpacked version that we've written up until now, and it was feeling pretty heavy and hard to move. So as soon as I can get this version to type check, I think we should be able to start doing some things. So what do we need here? We need kind signatures, because we have one down here for constraint. Constraint. What else do we need? We're going to need type. No, we don't need types in random instances. We need rank n types. Why don't I start up? Where am I? I'm in auth. And we're just in source. GHCID auth.hs. Go. Type operators. Language. There we go. Unterminated something. Go. Not in scope. Type variable t, because I probably chose a here. At. Type applications. And we're going to be building almost a parody of a Haskell application here in terms of the total number of language extensions we're turning on. Default signatures, monad trans. $67. It's not auth, it's proof. Tuple sections. Does rank n types imply scope type variables? I don't think so. Rank n scope type variables are needed to say that they're in scope in subsequent definitions. Rank n type says you can write rank n types. They both imply the for all syntax, but scope type variables lets that for all syntax do a little more. So the thing over here on the right hand side is GHCID, which is a program that's written by Neil Mitchell. Or GHCID. And so all I did was run GHCID and point at my program. Normally what I'll do is I'll run GHCID and I'll tie it to my current, it'll run cabal REPL or cabal new REPL. So yeah, BPAF has already supplied the link, so I don't need to. Multi-param type classes. What's next? Functional dependencies. Next. Language. Wish I didn't make that typo every time. Derive functor. EV. Apparently authentic, the T comes first. Could not deduce evident, TA. What do we need? Monad auth, T. N. M is SN. Monad auth T prime. T is T prime. Go. 46. I'll fix that in a minute. No instance of show for proof. Show now behaves like it did before. Showing a proof just shows the hash, it doesn't show the contents. One more argument to proof. Proof of A is showable. Variable not in scope. Control.monad exports app. $77. What else did I screw up? Unoff. Proof. A. Oh, I need to give back the A. No instance for show for verification. That's correct. Instance show verification A. Verification I don't really like. I almost want that to be proven and rather than proof, but whatever. And verified rather than. Okay, whatever. Verification of A shows prec D. Verification of A is going to be shows prec D. This is just actually the hash. Instance read, so we can read here, and that will matter because when we're unauthing, we'll be using the read side of this. This is read prec is verification using the GHC version of read prec. So we need text.read in order to get that beast. T with proof. Run prover. Why do I need this to be a proof? For all proofs? Well, that's annoying. For all M and T? There we go. Haha. So this might actually drive, this kind of thing might drive me to get rid of the fundep here and just use a type family. Like we could very easily, instead of doing monad auth TM, because if you look at it, the use cases that we have don't care what the T is, and so we're talking about types we're not using. So that's a good sign that maybe a type family would be a better way to do this. We could just say type auth M. And then we just want authentic for auth M. Evident auth M. A. That gets rid of my need for multi-parameter type classes, I think, completely. So we might need to switch some extensions around. Now instead of having monad auth prover, we have type monad auth, or type auth prover is proof. Type auth verifier is verification. And now we're not talking about crap I don't care about. And the type signature is down here. Non-flexible arguments, flexible contexts. So we pick up a need for an extension. But I bet we can get rid of that one. And that one. So we gained one but lost two. All right. How's that going? Import control monad state or trans state lazy as lazy. Let's just start building some instances just to see that we can transform existing monad auths and stuff like that. Instance monad auth. This is one of the reasons why I would maybe prefer this AI or API. Monad auth state TSM given monad auth for M. Type auth of state TSM is auth of M. And unauth is lift.unauth for lazy state. And maybe I should put this up here, wherever we defined monad auth. We need control monad trans lift, text read, hiding lift. All right, so we've built this will let you like work with state-teed auth computations and just unauth directly inside of them. So I'm trying to make this a good Haskell citizen. And so this feels like the Haskell-y version might be a bit nicer than the... But this is getting kind of repetitive. Type auth is auth, unauth is lift unauth. So let's see if we can... the default for this should be something like monad auth n. M is that. Auth of m is auth of n. Auth ma. Evident auth na. I need evident here. There we go. And so now this should just be defaultable. And that cuts the boilerplate down a line. So what have we done? We've now gained the ability to work with monad auth in the prover context and in the verifier context. And we can do it for state-teed transform provers and verifiers and stuff like that, so that if user code wants to start building up transformer stacks, they can. That's starting to sound Haskell-y. We'll get writer and reader and state and all this crap. What else do we have here? Oh, these need to know a monoid, or whatever it is. Should call them W, I guess. Blah blah blah. Strict writer WM, lazy writer WM. So for some monoid, we're happy. For monad auth M, reader T for some environment is fine. Reader T doesn't have strict and lazy variants, so we can just use it directly. I need to import control monad trans reader. Type indices must match the instance head. What did I screw up? Oh, I screwed up the rewrite in terms of W. Auth. Same thing. Yeah, there's no ID here. It's just this is just VI over here, and GHCID running off on the right-hand side. Learning monad style by reading one of my libraries. I'm not quite sure what you mean. Monads are W, this offends you. Sorry, King. What other monad transformers do we want? We want like RWST and all that crap, I suppose. Since this is starting to feel like something that monad auth M, monad auth, lazy RWST, RWSM. Boring. Lazy as strict. We just need RWS. What did I screw up now? This is RWS. Yay, the boilerplate of MTL. Metamon, if you can mention it to me later on or like drop it in IRC or something like that, I'll take a look. I just don't know what he means. But the others have the lazy before the strict. Oh no, what will I do? Lazy strict, lazy. Yeah, L becomes before S. Fine. Perfect. Okay, so we've got a pile of instances. We can do cont and a cum and a bunch of others later, because this is pretty generic. So now users can use monad transformers in their code. So that starts to feel pretty Haskell-y. And I also kind of like the fact that I can write this trust but verify and then just pass it the computation that I want to do. What else are we missing? Hey, look, it loaded. Trust but verify. What was our earlier computations that we were fiddling around with? We were doing like really simple things. Like we didn't even really test it past like this. Trust but verify. And so here's the problem where I was talking about before. I figured I was going to need to prove that I have evidence of auth and stuff like that. Once we moved out of the EDSLs that we had to trying to work against the generic API. So here we have auth for any value that we can read and show, auth. But this needs evident for me to be able to unauth as well. So I'm going to need the unauth equivalent of authv. And so what is this saying? This should say that I can take a T of A and produce an M of T of A. This should say I can take a T of A and give me an M of A. But T here is not authentic. It's auth MA, right? So what did we need? This needed, oh no, this works for any monad auth M. And this was auth M, auth MA is enough for me to give you an M of auth MA. And this is going to work with auth M. And this is going to work with auth M. For all M and A. Did I get all that right? Of course not. 63. Dict, and this is unauth. Hey, check it out. We managed to write unauth, auth, unauth, v. Okay. Trust but verify. Auth, the. This is auth. So I can authenticate any value, and I can authenticate any authentication. But I first need to unauth an auth, and then I can unauth v inside of it. And it actually believed it checked. Okay, so we were able to trust but verify. So we were able to, if we trust this computation, it produces this ugly-looking certificate on the right-hand side. Wow, that is a horrible-looking certificate. I don't know that I really like that format of a certificate. Let's see if we can come up with a better looking hash than that beast, shall we? So I don't really like that. Let's see if we can get a string out of it that's crypto hash SHA-1. What do you got down here? So that hash is hideous. Gave me a byte string. Maybe I should It is a SHA-1 hash. It's just filling the whole byte string. It's making full use. Do we have a little hex decoder encoder thing in Haskell somewhere that I can easily nice base 16 byte string? let's just grab this beast for right now for direct use in the command line without the GHC environment. Actually, GHC package describe base 16 byte string. What is it? Where are the modules? They are as soon as I can find my mouse. It's data.bytestring.base16. I did data.bytestring. Oh, because I do have a GHC environment. All right, what do we have here? We have encode and decode. That sounds lovely. So, since all I'm doing is storing that horrible-looking string somewhere in auth, data.bytestring .base16. So instead of showing it first, we're going to base16 encode the result of hashing lazily, and then we'll just show that stupid string. I only ever need to compute the hashes and stuff them in the certificate at the end, so I'm not too worried about it being ugly. Could not find the module data.bytestring.base16. That's because we're in a cabal file that doesn't know about it. We'll just build library auth, or just the main library even. Build depends. Base UTF-8 string, crypto hash 1. What was it? It was base 16 byte string. Exposed modules auth, I think we called it. And HS source dirs here is just source. Well, new build. Still building all the old crap that we're not using, but whatever. So we have the backpacked prover and verifier sitting here, but we also have the I didn't bring in transformers. Transformers also. And constraints. Oh no, we actually use constraints. Oh, we do for EAuth and EV. Do I use stack? Usually I use cabal new build these days, mainly because I like to. I have a lot of things I'm doing right now that use backpack, and stack doesn't support it yet. Control monad trans. I only use transformers, so I've got trans class. I can use G instead of colon. The thing is that is muscle memory, and I know the thing. I just haven't trained myself out of using it. Okay, so auth that cabal. We've got everything except for the fact that it's really saying it's annoyingly spamming me about the default language pragma. So I guess I could use common blocks now because we're on 2.2 or 2.2 or something like that. But cabal new build. What do we have? Do I write tests, property, and unit? Usually what I try and do is I try and make very, very strong types that then preclude me having to write tests. This is a kind of library that, because it's doing so much manipulation of values, it probably does deserve real tests. So I would probably quick check the ever-loving bejesus out of this thing. Are we going to have a Haskell 2020? I actually don't know. Herbert was doing a lot of work to try and make that happen, and I just really haven't heard much out of the Haskell 2020 committee lately. Maybe I just have been looking in the wrong places. Prover, verifier. We built auth. Git add source, git commit -a. Add non-backpacked version to repo. There. Now I've pushed it so that other people can look at it. Okay. So I've been down in the weeds. We now have a pile of compiling code. GHCID should now be able to just pop out of here and say, I want a cabal project file or something like that. Okay, I can cabal new build. If I cabal new REPL. Auth library. Auth lib auth. I have my auth. Okay. So I should be able to say cabal GHCID, and I should be able to pass it a command line. Cabal new REPL auth lib auth for right now. All right. So what do we have in our topics list here? Building a backpack, and we've built a backpack configuration. We've done this. Backpack or not backpack, we now have both versions to compare. I think we've come to the conclusion that to JSON and from JSON was the wrong version, and I think we've covered the general idea that quantified constraints would make a lot of this EV auth, EAuth noise go away. I would really just like to be able to call auth and unauth and have this crap just disappear. So the only ways I can think of to make that happen are to use like quantified constraints, where you could say class authentic T actually requires, let's go back to that again, for all A authentic or evident for T, T of A, and for all A, show A, read A is sufficient to prove evident T, A. This would be what I would like to write, and then I could kill this code, all of this, because then it's GHC's job to discover, oh, look, you're looking for evident for the same type. Go do it. Do I serialize Merkle trees? In this case, the trees that the only thing I'm ever serializing is a list of shown values. You could arbitrarily move to some binary format or anything else. And there's actually good reasons to use something other than a list. Like, for instance, what we might do is like maybe work smarter. The tree that we build could do the applicative actions of do the left-hand side and the right-hand side of the tree simultaneously, and then merge the answers together. So we could make Verifier smarter if we made our certificates more interesting. So you could use a little succinct thing that stored balanced parentheses and let you walk it. Or there's all sorts of tricks you could use that would make that fancier. So I don't have a particularly deep insight into what the absolute right way to represent my trees are, or my chain of evidence. I mostly thought this would be a fun toy to work through. So once we get quantified constraints, I really have a lot of hope that I could get away with this instead of this, and get rid of auth v and unauth v and auth and unauth auth. I think those are incredibly inelegant. The other way that I could get away with getting rid of them, maybe, would be to say something about how to do this. We could have tried to build up that atop, like in the backpack story. We still have the same problem of like needing to work with these evidence terms, but there we don't have a place to hang the quantified constraint thing that makes this problem go, theoretically could make this problem go away for the GHC'd version. So there we have the same kind of problem, but we don't have the way out. And so the only way that I could think of to make the backpack version cleaner... Oh man, what did I ruin? Oh, I need to keep you auth and EV. Would be to... Let's go back to the backpacked version and look at auth. Would be instead to provide something like... Provide proof of evident, or not evident, or provide a way to build evident for int and a few base cases, and then use that ability to like use generics or something like that in order to derive it for everything else. So there I would not gain the ability to just get this for free from show and read, though. And so I don't know that I like that. Another option is to just require show and read. Get rid of this evident concept entirely, and then just lie. We could just lie by not allowing you to read auth in the verifier. We could just have it always fail. And each one of these is a different point in the design space. I'm just not sure which one's the best. Like we're starting to see the parameters in the space. We can use backpack. We can lie or not. If we don't lie, then the API is harder to use. If we do lie, the API is easier to use, but you now have to worry about the fact that read violates the laws. But on the other hand, if you were to use binary instead of show and read, you get the same thing. Hey, Brian. All right. I'm going to take another 5-minute break here. Grab another Diet Coke, get up, stretch my legs, get out of these very hot lights for a couple minutes, and then I'll come back and we'll maybe use this thing for something, and then probably around 4 I'll hand off to Brian. All right, I'll be right back. That would explain why no one was responding. So what questions do we have on what we have so far? And I apologize to those who are talking on, anybody who's going to try and talk on Discord. I can hear you, but the stream can't. Subtiler, hi there. Welcome to the stream. Oh. So let me pull up my notes from earlier. So where are we at? We started off trying to build a small library for authenticated computation based on this paper that I linked earlier. Authenticated data structures generically, which I will relink in the chat just so that people who are diving in very late have some place to start. So this was the original paper. And then there was this post by Bob Atke, which turned around and built that as a library in standardml. And what we did was go off in Backpack and build a library that does basically the exact same thing in the exact same style as Bob Atke at the very beginning. Using Backpack as a proxy for all the ML functors that were in Bob's construction. And then I said, well, do we like the Backpack construction? I'm not sure. First of all, we started with JSON. We switched to just read and show. We built a Haskell style version of it. And the selection of tales was even prior to Brian starting to stream about doing Sonic-y things. So, anyways, so we now have a Backpack version and a non-Backpack version. I think in some ways, I think the non-Backpack version is easier to use and would be easier for us to write little examples against. I do think that quantified constraints will make this API more usable than it is today. As it stands, having to do separate auth things for auth and unauth, I think is a bit of a mess. Absolutely. So we've been sending, whenever I've been streaming, usually I run for about 4 hours, and then Brian starts up right after I do. And so try and raid him with as many people as will stick around for his stream as I can. So what do we have? So I just don't know whether or not I like having all this extra evident stuff. So let's do the wrong version of it, maybe. I think I like the non-Backpack version as well. I think being able to write trust and trust but verify as combinators rather than require users to use your API once and then instantiate is less of a mess. Quantified constraints let you talk about a constraint like for all A, monad or a monoid M of A. And so here, if we go look at the code that we now have on GitHub, and we look inside of auth.hs here, I have to do all this stuff to prove that show and read is enough to prove this evident constraint, whatever evidence is for my particular authentic data type. But then I have to do a lot of work to say, well, if I just have read and show, manually use this proof that this is enough to build evident and then use it. And that's getting really tedious. And I am totally in the wrong view. Thank you very much. Let's go back to coding. So I've been sitting here rambling, assuming that I've been looking at the coding screen this entire time. I really do need to get better at that. So I apologize. Alternative does not actually have enough laws to relate it to applicative, sadly. There's like 3 different sets of laws that alternative could have that relate it to applicative. Actually, like 4. There's like 3 that monad plus could have to relate it to monad, but applicative and alternative have an extra degree of freedom because they're not forced to be as causal as monads are. So the constraint here is not alternative. It's like and alternative is not just a monoid for all it. Like it's not just saying that M of A is always a monoid. It is that there's a monoid that has laws that relate it to applicative. The problem is that no one can agree on what those 3 laws are, and that it's useful to switch between versions that violate those laws. All right. So let's try a version of this that lies. Maybe it'll be nicer to work with. We've built auth. We've built the source version. Make dir lying. Copy source. Now that we've got this thing entirely self-contained. What does the lying version of this look like? Well, the lying version of this would kill evident, and it's just going to say that read and show is enough. And so we'll just have that. We're not evident with respect to some particular proof type. We're just evident. We don't need this crap. We're just that. And we don't need auth v and unauth, or auth auth. And we don't need any of this stuff. We're just evident. We need that. This is just saying that A is evident. We can take auth MA to get M of A. We don't need any of this crap. So I mean, being accurate has really cost us here. So maybe the lying version of this is better. We just say that we're able to read and show, and then we just fail to read. And then the proof, the read instance for the proof fails to read. Read prec equals empty. Some people don't believe that that should be associative. Well, that's a whole somebody else's peculiar madness. It's the unit law that breaks down, not the associativity. So this is the evil lie. This is the one that I've been trying to avoid this whole time, because we really want, if I show something and then read it, I get the same thing back. I mean, I could do something. I guess I could do something like this, like it's impossible to have this, and therefore this instance is okay. Yeah, so we have any. So if you can give me a proof of any, I will give you no. There. That's nice. Now you can't even get there. Well, no, because then you wouldn't be able to create. I need you to be able to construct the read dictionary, so I can't just do that. That was the thing that I could write that would pass the laws. You can't build this instance ever. But that's not good enough. So what do we got? We don't need evident anymore. We don't need EV. We don't need EAuth. That's all gone. Lying has saved us a lot of work here. EAuth, EV, all that crap's gone. Trust and verify is happy. We got rid of a lot of code. 111 evidence is gone. Import control applicative. All right, and now we wrote all that little test code where we were originally able to work with unauth and auth and all this stuff, and then we had to, when we moved to the Haskell version, we had to use auth v and all that stuff. But now I can go back to the auth 12, bind to unauth. And we'll do this inside prove, or no, it was trust. And what am I missing here? I'm missing auth ma is missing a show instance. Monad m. Why am I not knowing that I can show evident? Oh, crap. We have the same problem of not knowing that we can always show. We shared work here, but we did not actually get the proof that we can always show auth. So I was wrong. Damn it. I thought I was being incredibly clever. So we're not able to get rid of the auth. We were able to get rid of the auth v thing. So we still needed to carry around proof that auth. So eauth was originally our proof that that we know how to do show for auth, or show for T of A, and read for T of A. So we still need this thing, which we built forever ago. Let's go back to the non-lying version of the source code and steal the code for auth. So that's annoying. So all that lying did was get rid of one of the two problems. And then we have, down here, we have unauth. Auth. This is something like auth ma to m of auth ma or something like that, auth m. So if I have auth, this shouldn't really be a major concern, but whatever. So what do we gain? This is now monad auth. This is now eauth of no explicit definition of eauth. Here's proof. And then where's our other? We have authentic verification. We have authentic proof. Eauth is dict. So that's a thing. So lying has fixed one of our problems. Well, fixed it and made us just silently violate a show read law, but I think that's not too terrible. How else could we lie and fix up more problems? We could. This type synonym version was kind of nice. What if we didn't do that? What if these were actual data types? Now, like, the instances for the existing MTL would be more tedious. Auth and unauth is going to become more tedious. But we could hang instances. We could require show and read for auth m. Well, we would really want to require show 1 and show... shoot. Oh! Aha! So we built data types. We could move the authentic logic into monad auth. Would that be enough? So my goal here is to say provide proofs of show and read for auth m generically, so those are always around, and then we could have a version of this that is... So lying only got us halfway there. Let's go through and prove that that actually worked. So I was trying to trust this thing, and I wasn't able to. I had to at least do unauth auth, and this was auth auth. So we were able to actually compute a evidence chain and run with it. So we're able to trust. We're able to verify this computation with this certificate, and then trust but verify should run this computation both ways and validate that it both produced a result and validate and produced a verified result at the end. So this is a really ugly looking proof. We haven't built anything that's really worth using this library for yet. We've been doing toys that are just like, I have an authenticated authentication. But it's enough to make me spot warts. So unauth auth, auth auth. Fine. So make dir associated. Let's build one with class associated data and see how that thing looks. Copy lying. So now we are baking everything into auth m. Auth m will be a data type associated with my where were we? We had monad auth. This is now data auth m. And I want proof of evident for auth m and stuff like that in a very generic fashion, but that we'll deal with afterwards. What else are we going to need? We need show auth, shows prec auth. We'll take an int and a auth ma and give you a show s or something like whatever it is. Read prec auth will give you a read prec auth ma. And then instance of show can be written once and for all for auth ma. Shows prec is shows prec auth. Read for auth ma. Read prec. Read prec auth. And these hold as long as we have a monad auth for m. Now, all of my MTL instances are borked. And we have a whole bunch of other problems, like I don't want authentic auth m. There's no point in separating it because it's a different data type for every m. So I might as well move all the authentic logic into monad auth. And that's just this. So I don't really like this data because it's forcing me to be more repetitive than I want. But it does give me a way to get the show and read, even the lying read instance. And I'm hoping that I can use this to kill auth auth. Okay, so the dream is to have no auth auth and have no eauth. So now what do we have? We have monad auth, evident A, monad trans, monad auth. That's all good. The default for this does not make sense anymore. We can no longer default this. You have to write on-auth for every data type by hand. We have a shows prec auth, read prec auth, which are lies. Other than that, do I believe it? Here's a bunch of stuff that I believe up until this point. I believe show and read can be written generically for auth-m. I believe all those instances are dead and will have to be fixed. I believe I don't need this. Proof is now going to be associated data here. So data auth prover is proof a hash. This is now shows prec auth. This is my read prec auth. This dies. The authentic proof lives here. Unauth auth doesn't exist anymore, and we have a prover. So prover is applicative monad. It's a monad auth. It has this stuff in it. So writing all the MTL instances is now going to be 5 lines, but hopefully we're not going to clutter up user code with unauth, auth, etc. by doing a little bit of lying. It also means that we're going to have to be a little more careful about like user code, like going in and out of the monad for working with my individual transformers. So what do we have now? So verification for verification hash, authentic verification is now going to live down here. Auth, data auth verifier is verification hash. So that's my verification data type. Shows prec moves in here. We're willing to read prec, and we're going to have to read prec, so this thing can actually succeed. Reads prec auth is that. We don't need this dictionary construction. We've got the auth, which we copied. So we have a verifier. Run prover, trust but verify, all of this stuff should in theory still work. It's going to complain about a bunch of unused packages. Auth for verifier takes an extra argument. This can be a new type instance. I don't have auth anymore, it's just unauth. Auth. Woot! Alright, we managed to kill all of the constraint kind nonsense. So in theory, we can drop the use of data.constraint completely. Hopefully building a little library that end users might want to use. All hinging on one little lie. And now we'd have to go through and build like data lazy state auth and all this kind of stuff. So how would this work? There's going to be an auth lazy state MA, and auth is going to be auth dot hello tedium. Unauth is unauth lazy state. Shows prec auth. D is shows prec auth d dot unauth lazy state read prec auth is auth lazy state read prec. Let's get one monad transform we're looking. See if we can spot a pattern. So this is an auth MA. New type instance. What did I screw up? Auth needs to take this thing, A to auth MA. We auth, and then we wrap this thing in an auth lazy state. Yes. Unauth needs to take an auth thing. This is going to be like lift or something like that. All right, we've managed to build one instance. Okay. These are all going to basically be the same boilerplate, and I have no way to share code. I could write a template Haskell bit or something like that. This is the lazy one. So this is the problem that I have with this approach. It's like, I get rid of all the boilerplate, but now I have to write these things. I don't know that it was a win, but it probably is a win for end users. Strict writer here's auth for reader. Auth lazy state, lazy RWST, more boilerplate. And I did the strict one when I should have been doing the lazy one, but that's okay because I just needed the lazy one down here anyways. Alright, that could have been fancy little template Haskell nonsense, but whatever. So we've recovered all of our MTL instances, they're just 4 times longer or something like that. So we have a prover, we have monad auth, we have a verifier. We can trust but verify, we have monad auth, we can write code generically, we can use auth and unauth. We don't have to work with unauth auth and auth auth. Is it resistant from the empty tree, eavesdropper, modify the auth if it's hashes and data? If you try and come in the middle and change the authenticated data structure that we built, it will fail to validate. Let's try it. So we did a trust but verify of that, but let's just trust it. And take this thing and first run it through the verifier by hand. And what do I want to verify? I have the computation that I want to verify. I want to verify this. And along the way, let's first of all try and change this value, and it says it failed. Or let's try and go back here and change the hash. So intervening in the middle And changing the output here is going to require you to be able to compute a hash. That you would have to do the work on whatever it is that you want. So if I tossed you an authenticated data structure that I know the hash of, and you toss me back a result that starts from that thing, I can validate the bits and pieces that I want to validate. Does that make sense? If, on the other hand, you want to make up your completely new data structure, and I know nothing about the data structure that you're working with, then I would have to worry about, like, you did a search on a completely different thing because you told me the hash of a data structure, but didn't actually give me the data structure. You just said, hey, I did a lookup in a thing, and here's its hash, but you don't know anything else about that. It can't change. Yeah. So the person who's on this side might know the say I know the tree. I know the hash of the tree that we're going to work with. We agree on a tree. Here's a computation that I want you to perform on this tree. Go. You go perform a computation. It comes back to me with a certificate and an answer. And we go. And so we might need to do some work in order to agree on the data structure that we're going to be computing on in the middle or at the beginning, but you can't just change the data that you're going to work on. Would this work for procedural computations if you could formalize the side effects somehow? Sure. You could just build a heap that is built as a map that holds onto authenticated data in the cells. So now that we've got some stuff, we can actually build something on top of this thing. So let's do it. Damn it. Spent so long trying to figure out what the API looks like. We're going to run straight into poor Brian's stream. Let's build like a little Merkle tree or something like that actually is authenticated. So we've got like tips. They just hold on to values. Maybe they're authenticated values. I don't know. I'm going to tie it to the monad. And I might have bins that have authenticated Merkle MA. It doesn't make a tree. So this is the other thing that I don't particularly like about this version is that like the notion of authentication percolated into all my trees. But whatever. Auth M. How these became trees. And maybe I don't authenticate the leaves or something like that. I just say you walked past this thing. So we've got a tree. And what do we want to do to the tree? I want to give you lookup in the tree. Given a tree MA, I will give you an M of maybe an A. And I need to give you a path or something like that. Which way do you go in the tree? So I didn't bother to. I haven't built keys or anything for the tree, so I'm just going to deal with like walking down a path of left-right directions and stuff like that. So what will we do? If we look up and we have the empty path and we have a tip A, this is going to be return just A. We successfully looked up a path in the tree. Done. And here what we're going to do is we're going to come down and yeah, you could work with fancy little free monad-ish things. The thing is that tree MA is not a functor because auth M is not covariant. At the moment, we would have to do more. Like for instance, when you're working with the particular choice of auth M for a proof, this can be covariant because I have enough information to like actually recompute it maybe. Well, actually it can't be covariant. You'd have to actually know the constraint. But what do we want to do? We want to look up false x's in bin L R. Well, first of all, we're going to have to unauth L. Maybe what I want to do is, instead, I want to wrap the whole data constructor in and off. Let's figure out a way to do this. T of A is going to be bin AA, tip A, or bin BB. Let's do that. And then a new type, tree MA. I'm still working out the bugs here, or figuring out how this should work. Run tree should give me back a auth of a T A tree MA. Does that look better? And then we'll fix up lookup. So now we'll have authenticated tips as well as bins, which is kind of nicer. So lookup in the empty path, or lookup a path in this tree is going to be first unauthenticate the tree, and then case analyze it. And if it's a let's see here. Case P and tree, well, if the pattern is the empty list and the tree has a tip containing an A, I'm going to give you just an A. On the other hand, this has to be a return. If the pattern is a left and the tree is a bin LR, it's the rest of the path. We're going to look up using Q in L. True. Look up using Q in R. And any other pattern applied to any other thing, fail the lookup. Yeah, bin is a non-leaf tree node. So it's just a branching tree. So this is a tree that is made out of bins and tips, and each level is authenticated. Well, what I could do is I could send you. We can envision a world in which we had different notions of different users performing authenticated computations, perhaps, where you have Alice and Bob don't trust each other completely and want to validate each other's portions of the computations. I think that'd be an interesting little exercise. I think you'd need a slightly different API than what we have here, but I think you could do a multi-party version of this. Right now, we just have a single untrusted compute node and a verifier that we inherently trust. But an idea of an Alice and Bob that both want to validate each other's work, I think, is very interesting. And so instead of like having one certificate that I'm producing and one that I'm consuming, maybe I have the certificate for what Alice did, and I have the certificate, like for all of my parties, all their certificates. And I'm a consumer on everybody else's certificate, and I'm a producer on mine or something. And when we get done, we all toss certificates over the wire, we all check each other's work, and then we call it good. That would be fun. I have not actually thought that through. I think you've got a publishable paper there. So what have we done? We built a lookup. And then let's just make some functions. Tip takes an A and gives me a tree M A for monad auth M, and anything I can that is evident. Tip A is take this, auth it, and then put it in a tree. Bin takes two tree MAs, builds a tree MA. Just needs monad auth m. Bin lr is tree of auth of bin lr. Wrote a typo. Forgot to end that. T. What did I screw up? Auth m. No instance of monad m. Where did we screw that up? We didn't know monad auth m. Could not deduce show for T. What else I screw up? Could not deduce show of A. I need to know more about A. I need to know that A is evident. Could not deduce show for tree MA. What do I need for this? Well, just deriving read and show. Data constructor not in scope. Off, because it's not a data constructor. Well, maybe it should be. Now that we're lying, we can actually do a pattern synonym for auth. What is auth going to look like? Auth looks like if I have evident A and monad auth M, then this will take an A and give me an auth MA. Pattern auth A is, well, it's as long as we can unauth. No, I can only construct with it. That's right. I can't view with it. That's okay. It's a pattern we can. Nah, it's not worth it. Okay. We have a smart constructor, but not a smart batch. I started trying to do this at one point, and it failed. Show A, arising from the use of auth. We need to know evident A, apparently. Don't know why. Did I need show in any way and shows prec auth and... Monad auth m, show and read, auth ma. I don't know why I needed that. I shouldn't need any evidence on bin. I don't know why. Bin, tip 1, tip 2. Trust. Lookup. Just the false branch, or the left-hand branch of bin, tip, true. Okay. Look up just the true branch. So here we're looking at the tree. It says we have a tree. It's got this hash. And when I match on it, I get another tree. And when I match on that, I get this tip. So we've managed to build the evidence trail that we want. And then if I were to build like a little layers in... I don't know. What's a good way to build a nice binary tree that is full of stuff? Functor version, all recursion schemes. What's the pattern keyword? The pattern keyword makes a pattern synonym. The idea was to make a smart pattern. The problem is that the smart pattern has to return a result in M, but but produce results in the normal thing, and so it doesn't quite work. Would it take me long to make a tree visualizer? Maybe, mainly because I don't have... When I show these trees, they don't actually see the original tree. Like, given a tree MA, I can walk into it, but if I were to show it, it doesn't show very prettily. It just shows the one layer. Or it shows... It's just a hash. From what you can see. So what can we do here? Let's do a failed lookup. There's proof that this is nothing. And if I go too far down a branch, it should also be proof of nothing. Oh, so meet them on. So what we're doing is, how to describe this? There's so it's about an hour since the last time I've kind of described what the heck the mission is here. I might as well repeat. And we're slowly getting to a point where we can wrap anyways. So what we've been doing is this. There was a paper in 2013 that talked about how to build a programming language for authenticated computation. And the language that they described had semantics where they described, hey, here's how to produce the answer and a certificate on the server, such that on the client you can just run the computation with slightly different semantics with the certificate and validate that the server did what you thought you wanted it to do. Like that it walked through the parts of the tree and looked at them and computed the answer. And the idea here is that whenever you go through one of these like auth type constructors inside of a data type, you're like passing through a gate. And then you can, you're using the certificate to validate the result of what came in and out of that gate. And so the end goal is to get you sort of something that feels like roughly like the certificate should be like roughly log-ish in size, and is built by using Merkle trees. So what we're doing is we're computing these Merkle trees, in this case just using like show and read and like very simple Haskell classes, and we're using a lot of high-powered machinery to make it go. So at the very start of the stream, I started trying to build it up with Backpack. I didn't really like the design that we got out of Backpack in Haskell. And then we've sort of gradually walked it back to a more Haskell-y design that is much heavier, but was inspired by the smaller Backpack design. And so we had to do one bit of lying and accept a few things. But now we're getting to a point where we've got a pretty good general framework for doing authenticated computations. So now what we can do is we can write a computation that, like in this case, is like working with these little trees. Like if you give me a tree that has like these two values at the leaves and some path into it where the path is described as false goes left and true goes right, walk down this tree, what's the value at that node? I can give you the answer. And you can trust me that like if you look at the trees that came out of the computation, at this point in time I'm building a tree with no like evidence trail. Like about what I built, but I can't lie to you. You can actually validate the individual steps of everything I've done. So that's, I think, we've done a really cheesy tree example. We might be able to define like a set or something like that takes run it off M, evident A, takes a path and an A, and a tree MA, and gives you an M of a maybe tree MA. Update this path to this value in this tree. And this can't change the shape of the tree, but can scribble down in the inside of it. And so with a little bit of additional sugary bits, you could go through, and instead of having these be tips and values, you could just like put values in the binary constructors for like what are the values here. You could then do binary tree walks and validate that like they haven't violated your assumption that this is a valid data.set or something like that along the way. That everything that they looked at looked like maintained all the invariants of my data structure along the way. Those might be more interesting validations and stuff like that you want to perform. Okay, so any remaining questions? Otherwise, I think I'm getting ready to start handing over to Brian. So Archine Mind. So generally, what I was trying to do was stream every week. I'll stream again next week. And so I've been trying to aim for like doing noon on Sundays. My travel schedule really got in the way for almost the last 2 months straight, which really hurt. When will I next give a talk at Boston Haskell? Hi, Dan. Maybe next month. So talk to me offline, and then we'll see if what makes sense to give a talk on. All right. So Brian, do you have your stream up? If you do, I can raid you. If not, it's very difficult. All right. So what I will do is I will randomly dump everybody here on Puff and Fresh's stream. He's been working on streaming like how to put it, accessing all of the guts of Sonic 2 in Haskell. So it's a deep dive from sort of like the theory land where I've been playing into how to actually like use Haskell to manipulate images and do all the nuts and bolts of fiddling with an old, I guess 16-bit title or something like that. All right, here you guys go. And I will stop recording.